Welcome. We have been discussing radiation, and in the last class we discussed how you could describe the energy that is being carried by a ray, and I told you that this could be described, this could be quantified in terms of the specific intensity or the brightness, which is denoted by I nu. And this quantity is defined for a for a ray we have a particular specific intensity, and we have defined the specific intensity in such a way so that it tells us the following thing: if we place an area element of size dA normal to the direction of the ray and ask the question, what is the energy coming into this area element from the solid angle interval d omega in the direction of the ray. So the energy incident in this ray is given by the specific intensity into the area element, into the solid angle, into the time interval, into the frequency interval. So this tells us, the specific intensity tells us the energy incident that is being transported by this ray, which is also the energy that is incident on this area element dA from the solid angle d omega. So it's from a specific direction, range of very small range of directions, in the frequency interval d nu, in the time interval dt. That's how the specific intensity is defined. So this is called the specific intensity or brightness, and this is what we use to characterize, to quantify radiation. Provided you are dealing with length scales which are much larger compared to the wavelength, where we can think of light as rays. And then in the last class we studied certain properties of this specific intensity. I told you, actually I showed you, that it is conserved if light propagates in vacuum. So if light propagates freely in vacuum, the specific intensity does not change along the ray. Right, we saw this in the last class, and we saw various other things that you could calculate. Once you knew the specific intensity, you could calculate the flux, you could calculate the pressure, and various other things. Today we had, in the last class we had just briefly started discussing what happens when light propagates through a medium, and that is what we are going to discuss in today's class, right. So let me start off where we had, let me just briefly repeat what we had discussed right at the end of the last class. So we were considering emission, the emission of radiation. So we are, our attention is on a particular ray, and it is traveling in a medium. So this is the medium, and our ray is not in a single direction, it is in a small range of directions, so in the solid angle interval d omega. So this is what we are interested in the solid angle interval d omega, in the frequency interval d nu, in the time interval dt. That's the energy that is incident. So we are interested here in rays traveling in the solid angle interval, directions in the solid angle interval d omega, and it is, the light here is propagating through a certain medium. So the incident energy, we have already calculated this. Let us say that this has a volume. The incident energy is, let us first calculate the incident energy. Let us use S to label the points along the ray and this is S plus delta S. This point is S, this point is S plus delta S, ds you may say, okay, S plus ds. Now the incident energy on this surface, let us call this surface dA, we just saw how much the incident energy is. The incident energy is I nu at the point S into dA d omega d nu dt. Now we next define something called the emission coefficient J nu. So this medium through which the light is passing is also emitting radiation. So when the light comes out, the energy that would come out would be the light that is incident, the energy that is incident plus whatever has been emitted by the medium in between. Now the emission coefficient is defined in such a way so that J nu into the volume element. So here what's the volume? The volume here is ds into dA. This is the energy that is emitted out in the solid angle interval d omega, in the frequency interval d nu, in the time interval dt. So the emission coefficient tells us the energy that is emitted in a particular solid angle d omega, in the time interval dt, in the frequency interval d nu by a volume dV, where here dV is dA into ds. That is the volume that the light is going through. That is what gets added to this ray. Okay. So the light that comes out is now the specific intensity, sorry, A nu at the point S plus ds, and everything else remains the same. So with this definition of the specific intensity of the emission coefficient, it essentially tells us per unit volume the energy emitted per unit in that particular per unit frequency interval, per unit time, per unit volume, per unit solid angle. Okay. So with this definition of the emission coefficient, the difference in the specific intensity in the length interval ds is J nu. So from this we can straight away say that di nu ds is equal to J nu. So when the ray traverses a distance ds through a medium with emission coefficient is J nu, the specific intensity, this is the rate at which the specific intensity changes, okay, or this increases by an amount J nu ds. Okay. So this is the emission. So we model the emission process. Here we are not going into the microscopic detail of how the emission occurs, right. We are not going into the microscopic detail of how the emission occurs along the ray. We are just quantifying whatever mechanism you have through this emission coefficient, which tells us that per unit volume, that is the energy emitted in this solid angle d omega, in the frequency interval d nu, in the time interval dt, which is of our interest. Okay. So this is, and as a consequence of that, the specific intensity changes like this. Let us now quantify the absorption. That is the other possible process. So we are looking at absorption next. Okay, that's the next thing of our interest. And here so we have the same thing, we have a ray which is propagating, and it goes through a medium. So and the question is, what happens to the specific intensity when the ray has traversed through a length ds through some medium? It will get absorbed. In general, there will be emission and absorption both. So how do you quantify the absorption? And for this there is the something called alpha nu, which is the absorption coefficient. Okay. Here again let us go through the same exercise. So the incident energy per unit, we are interested only in a certain solid angle. So the incident energy is I nu into dA d omega d nu dt. Now the energy that gets absorbed here, this is at the point S. Okay. So at the point S, and the energy that gets absorbed is alpha nu times I nu into dA, the volume. So the absorption, the energy that is removed by a volume dV, is alpha nu into the incident specific intensity into the volume. Again we have all those elements, the solid angle, the okay, and this is equal to the specific intensity at the point S plus ds So the absorption process, again doing the same thing. So the absorption process now gives rise to a decrement in the specific intensity, and the decrement we see is di is given by di nu ds is equal to minus alpha nu I nu. Okay. So let us try to just get a picture of this, of why we have written it in this way, that it is proportional to the incident specific intensity into some absorption coefficient. So consider a hypothetical situation where we have a volume, this is the volume that we were interested in, dA ds, and in this volume we have small absorbers distributed, microscopic absorbers, and each of these absorbers has a scattering cross section of sigma nu. That is the scattering cross section, it is the area which each of these microscopic absorbers, these small absorbers, that is the scattering, that is the area which it through which it absorbs. So the incident energy is, let us just ask the question, what is the total area that is actually absorbing? So these absorbers have a number density n. Okay. So let us assume that there are these small absorbers with number density n. So n of these absorbers per unit volume, and each one has a surface cross section area scattering cross section of sigma nu. That is the area which it presents for absorption. Okay. So, let us ask the question, what is the total area covered by my absorbers in this volume? To do that, we have to take the number density and multiply it by the volume. So, that is the total number of absorbers. Each absorber has an area sigma nu. So, that is the total area which is presented by these small absorbers, and the total energy that is absorbed now is going to be the I nu, the incident specific intensity, into this area, into the solid angle, into d nu dt, right. So, this is the energy loss that is going to be caused by these small absorbers located over here, which with number density n and scattering cross section sigma nu, right. So, which is why we have written it, which is one picture which kind of gives us a feeling for why we have written the scattering the absorption term as the incident specific intensity into some absorption coefficient, and here we see that the absorption coefficient can also be written in terms of the scattering cross section of these individual microscopic scatterers, and it can be written like this, where sigma nu is the scattering cross section, the area of each of these small absorbers, and n is the number density. Okay. This is also quite useful sometimes when we know the scattering cross section of the individual microscopic absorbers. So, now we are in a position to combine both of these and write down the radiative transfer equation, which tells us what happens to the radiation as it propagates through a medium. Okay. So, let us write down the radiative transfer equation now. So, this is called the transfer of energy through radiation, radiative transfer, which is very important in astrophysics, and the equation now has, we are interested. So, this is the situation that we are considering, is that we have a ray of light. We are interested in a particular ray of light. S is some distance parameter S along the ray, and the equation, radiative transfer equation, is the derivative of the specific intensity with respect to S. So, there will be an input of energy due to emission, and that is given by J nu, and there is a removal of energy which is given by minus alpha nu I nu, right. So, this is the radiative transfer equation which governs the propagation of radiation, with which we can use to study how radiation propagates through any medium. Okay. So, the rest of this class is largely going to be devoted to the discussion, to the analysis of this equation, right. So, let us start off by discussing two simple situations. The first situation is where we have only emission. So, if you have only emission, so this is going through a medium. So, we have a medium over here, right. So, as the light propagates through a medium, the absorption, we can, let us suppose that the absorption is very small, it may be neglected, and it is the emission that is important. So, the light is propagating through this medium, it is the emission that is important. In that situation, we can forget about this, and then we have I nu. This, let us say, is S equal to 0 when it enters the medium, okay, and we are interested in I nu as we go along the ray. So, this is increasing S. So I nu at some point s is I nu at s equal to 0 plus the integral 0 to s. Now the emission coefficient can vary inside the medium, it need not be a constant. So I have a j nu s prime ds prime, and if it is a constant, then the problem is very simple. I have just got the emission coefficient into the length. Okay, so that's how the specific intensity increases there. Okay, so that's one of the simple situations. The other simple situation which we encounter quite often is where you have only absorption, and we encounter this very often. For example, light is propagating through a slab of glass, or through some water, or through the atmosphere when we look at the stars. So in any such situation, you typically, it is absorption which is important and not the emission. So in such a situation where you have only absorption, here again the solution is rather simple. So here we do not have the emission term. So you can bring this I nu onto the left hand side and integrate this, and we can straight away write down the solution without going through the mathematics. The solution is I nu s, so s is some point inside the medium, is equal to I nu 0. So when you bring the specific intensity onto this side, you will get a log of the integral of alpha nu into s ds. So when you invert the log, you get an exponential. So this is the incident specific intensity into exponential minus 0 to s alpha nu s prime ds prime, right. So it decays exponentially. If the absorption coefficient is a constant, then it just decays exponentially with the increasing length, minus alpha nu into s. Okay. So this is how the specific intensity changes with the increasing distance inside this. Now we are interested in a situation next where we have both emission and absorption. So the question is how to solve the equation, the radiative transfer equation. In such situations, it is convenient, it is very convenient to introduce something called the optical depth. So let me introduce the optical depth. And we use the symbol tau to denote this quantity called the optical depth. And this is a very useful and a very interesting quantity if you are doing radiative transfer. Okay. So this optical depth, so the way we proceed is that we divide this equation with the absorption coefficient alpha nu. Okay. If I divide this equation with the absorption coefficient alpha nu, then we have in the denominator over here we have d tau is equal to alpha nu ds. Okay, and this is called the tau is the optical depth. So we can integrate this and determine tau. So tau, the optical depth, it's a function of s obviously, and this is 0 to s alpha nu S prime ds prime. This is the optical depth. Okay. So, we are interested in the propagation of this light into this medium. S is 0 over here, S increases inside, and the optical depth is the integral of the absorption coefficient into ds as you go inside the medium, and you integrate till the position you want to calculate it at. Okay. Now, what does the optical depth tell us? Let us take a look at this. Okay. So, to get a clear picture of this, there are a medium is said to be optically thin, or optically, okay. If tau is less than 1, a medium is said to be optically thin. So, it is said to be optically thin. So, let us see what it implies. You see this term over here, what happens to the specific intensity as you go inside the medium? It falls off exponentially, right, and it falls off exponentially as e to the power minus the optical depth. So, if the optical depth is small, say my medium is only this much and my optical depth is small, so this is a small number. So, my specific intensity, whatever goes in, largely comes out. There is very little loss inside, right. If this number over here is quite small, is very small, then the exponential is very close to 1, and whatever goes in roughly comes out. There is a very small attenuation inside. Or we can say that the chance of a photon which enters this medium coming out without being absorbed is quite high. Right? The average photon does not interact with this medium, does not get absorbed with the medium, by the medium. It just goes through and comes out. Okay, so this is what is called optically thin. This is a medium that is optically thin, and we would also call it transparent. Okay. So, the typical, in such a medium, the typical photon just goes through the medium without interacting with it, without getting absorbed. Okay. So, typical photon here just goes through the medium for an optically thin medium. It is transparent. The typical photon goes through the medium without experiencing any absorption, without interacting with the medium. Such a medium is said to be optically thin, and this is measured by this quantity tau. Okay, such a medium is said to be transparent, and this is measured by this optical depth tau. Tau greater than 1 it is optically thick. So, such a medium is said to be opaque. What do we mean by this? So, this is the optical depth, and as the radiation goes through the medium, its specific intensity falls off exponentially, and if this is a large number, then it would fall off considerably. There would be a considerable drop inside. So, the typical photon essentially cannot propagate through the medium without being absorbed. It is guaranteed to get absorbed inside. Okay, if tau is greater than 1, the typical photon in general gets absorbed in the medium. Okay, so this is the significance of this quantity, the optical depth. It gives us a picture. It essentially tells us the probability of a photon getting absorbed in the medium. If the optical depth is small, the probability is small. If the optical depth is large, okay, it quantifies. The probability is essentially exponential of e to the power minus tau is the probability. Okay, so this quantifies whether a photon will go through the medium without getting absorbed or whether it will get absorbed in the medium. Okay. and if it is much less than 1 it is transparent, if it is of the order of 1 or more, if it is more than 1 it is opaque. So this is the optical depth. So it is convenient to write down the radiative transfer equation in terms of the optical depth. We also define another quantity called the source function. So if you divide this by alpha nu, the equation now becomes, let me write down the equation, the same equation now becomes so we have divided this equation by alpha nu and written this term first, which gives us I minus I nu, and we have this S nu, where S nu is called is the ratio of the emission coefficient to the absorption coefficient, and this is called the source function of the medium. Okay. And quite often these are very useful quantities, both of these, the optical depth and the source function, and it is convenient to think of everything now as a function of the optical depth. Okay. And the optical depth is a very useful quantity. It tells us it is convenient to think of this equation in terms of the optical depth. It tells us the appropriate intervals as far as the interaction with the medium is concerned. Okay. So that it quantifies the appropriate intervals along the ray as far as interaction with the medium is concerned. The length may increase a lot, but if the optical depth does not increase much, it is of no relevance for the propagation of the radiation, because the specific intensity is going to remain same. Whereas if the optical depth changes drastically over a small length, then it is that interval which is important, right? So if you work in terms of the optical depth, you are now going to see the lengths, the intervals that are important for interaction with the medium. Okay, so that is one of the very great importance of using the optical depth. Okay, so we are going to work in terms of the optical depth. Everything here is now a function of the optical depth and not of the length along the ray. Okay, everything is a function of the optic tau. Second thing is the source function is a ratio of the emission coefficient to the absorption coefficient. Quite often this is a physically simpler quantity to calculate than the emission coefficient itself. So this also has got great utility, the source function. Okay, so we are going to solve this equation in the radiative transfer equation in this form. The way to solve this equation, so we are going to work out a formal solution to this equation. The way to proceed is as follows. We multiply this entire equation with e to the power tau. So let us multiply this equation with e to the power tau, and we define so let us do that. So if I multiply this equation with e to the power tau, then I can write it in this way. And we can now integrate this equation straight away because we have a known, this is what we want, this is a known function on the right hand side. We are assuming that the source function is known, so this is a known function on the right hand side, this is unknown, we want to find this just integrate this. So it is quite straightforward now to write down the solution, just integrate this with respect to tau and then divide throughout by e to the power tau, and we will integrate from tau equal to 0 to some value of tau. Okay. So, I will write down the solution straight away. The solution is I tau is equal to, so we are going to integrate this equation from 0, 0 is where the light enters the medium and tau is the value of the optical depth where we are interested in the specific intensity. So, this will be equal to e to the power minus tau I nu 0. At tau equal to 0, this term does not contribute. So, when I divide by e to the power tau, I get e to the power minus tau I nu 0. And we have one more term which is this into an integral, which is I have to do the integral 0 to tau, the integral of the source function. So, S nu tau prime e to the power. Now, you see I am doing this integral and the variable is now becoming tau prime. So, I have e to the power tau prime d tau, but I am going to divide with e to the power tau at the end of the day. So, we can write this as e to the power minus tau minus tau prime d tau prime. Right, that is the formal solution. Okay. So, this formal solution to the radiative transfer equation. So, we have solved it in general, but life is not so simple. Okay. So, the formal solution does give us something, but it does not always not very easy to apply in all situations. Okay. Let us first physically interpret this equation, the formal solution. What are the two effects that have gone in? So, the first thing that you see is this term over here. So, let me draw a picture. This is my medium on this side. This is tau equal to 0 and this is the ray that we are following. So, at tau equal to 0 we have some incident specific intensity I nu 0. As it goes inside, we are interested, let us say, at this point. So, as it goes inside, it gets attenuated by an amount e to the power minus tau, which we have just seen. That is the solution when you have only absorption. So, which is the first term that you have over here. Whatever is incident gets attenuated by an amount e to the power minus tau, where tau is the integral of this absorption coefficient along this line. The second effect that you have is that each point over here is itself going to contribute to the specific intensity, and that is going to contribute by this source function. Okay. So, the point over here at some tau prime is going to contribute, and it is going to again suffer an attenuation, that is not the entire tau, but the difference tau minus tau prime by this much, right. So, we have to take the source function at this point and attenuate it by e to the power minus tau minus tau prime, and then add up the contribution from all of these points, which is this term over here. Okay. So, this is the contribution from the radiation along the path, and each point the contribution gets attenuated again as it propagates through the medium. Okay. So, this is the formal solution to the radiative transfer equation. Now, as an example, let us, so we can first of all straight away see that we recovered the very simple situations that we had considered right at the start, where there is only emission and where there is only absorption. Those you can recover straight away. Let us now consider a situation where the S nu is a constant. It does not change with position, it is a homogeneous medium. The source function is a constant. So we are going to assume that S nu, the source function, is the same throughout this entire region. Okay. If the source function is the same through this entire thing, we could then do this integral. This term will come outside, and e to the power minus tau will also come outside. So we have an integral of e to the power tau prime d tau prime, right. We have just an integral of e to the power tau prime, because this minus and minus sign here, e to the power tau prime d tau prime, and the limits of the integral are tau to 0. So if you do this integral e to the power tau prime, let me write down the integral. So we have the integral, the second term now becomes e to the power, this s comes out, e to the power minus tau comes out, and we have e to the power tau prime d tau prime, right. That is the second term. The first term is unchanged anyway, the second term becomes this, and this can be written as s e to the power minus tau, and we have e to the power, the integral of this is again e to the power tau prime. So at the two limits we have e to the power tau minus 1. Okay, so this is s 1 minus e to the power minus tau, right. So we have just evaluated the second term, and we can now plug it back in this. So if I plug it back in this, what do I get? I get the fact, the solution is that I nu, the specific intensity, is the so we will have a constant term S nu. Yes, the subscript nu is there throughout. It's at a particular frequency. So this is going to be S nu plus we have this term already here, and we have this term which has to be added to it. So what we get is plus I nu 0 minus s e to the power minus tau. Okay. So that is what happens when light propagates through a medium which has a fixed source function. It does not change with place. Okay. Let us try to understand what happens. So the light, when it enters this medium, its specific intensity is I nu 0. The source function is S nu inside. Now let us see what happens here. As it goes deeper and deeper into this medium, the value of tau increases, and as the value of tau in the limit where tau goes to infinity, tau is very large, the specific intensity then becomes just the source function. Okay. So given sufficient optical depth, the specific intensity will tend to the source function. It will relax. This is a relaxation. the value of the specific intensity will relax to the value of the source function. So, provided there is sufficient optical depth. Okay. So, if there is sufficient optical depth, the specific intensity inside the medium will tend to the source function. It will just be equal to the source function, whatever it comes in with. If it comes in 0 also does not matter, it will finally just become the source function inside, provided it is optically thick. Okay. Now, so that is the first thing. So, the first property is provided the optical depth is very large. The second point, suppose the light enters a medium where the source function is more than the specific intensity. So, the light here is entering a medium where the source function is more than the specific intensity of the ray. What happens then? The medium essentially pushes the specific intensity up, right? That is what we see here, it pushes the specific intensity up. So, this implies that the specific intensity will go up inside that medium. Similarly, if the specific intensity is less than, if the source function is less than the specific intensity, it will bring it down. And given enough optical depth, it will bring it to exactly the same value as the source function. Okay. So, the source function drives the specific intensity up. If it is more than the specific intensity, it brings it down if it is less, and given sufficient adequate optical depth, it will bring it to the same value. It will relax to the value, same value as the specific intensity. Okay. So, this is a rough picture of what happens when radiation propagates through some medium where you have both absorption and emission. Okay. So, picture is quite simple, but its life is not so simple. Okay. There is a process called scattering, which we have not discussed. We have not discussed any specific process as yet, but scattering makes life very complicated if you are dealing with radiative transfer. Scattering, if you have scattering, the light that is incident gets spread into different directions. So, the emission coefficient or the source function is essentially related to the incident specific intensity. I cannot specify it a priori, right, because the light, the source of the light is the incident light itself in scattering. In scattering, light comes in and it gets scattered into different directions. Okay. Example, light is propagating through some, say let us say glass which is which has rough surface, okay, glazed glass. So, the light that is incident itself gets scattered in other directions. So, that is again a source for the light in some other direction. So, the source itself is dependent on the specific intensity that is incident, and this makes the problem extremely complicated. The formal solution is just a solution, but you do not know then what this S nu is. It is dependent on the I nu. Okay. So, you cannot, this is of not much use there. Okay. So, having discussed this, let us now ask the question, what is the mean free path of radiation inside a medium. So, this is a medium, the radiation is propagating, this is radiation incident on a medium, again same question. Okay, I have a picture over here already. So, there is radiation incident on a medium. We know the idea of a mean free path. On the average, how much distance does a photon propagate before it gets absorbed? That is the mean free path. How much distance does a photon propagate before it gets absorbed. Here we are talking in terms of distances, not in terms of optical depth. Okay. So the question is, how much distance does a photon propagate inside the medium before it gets absorbed, a typical photon on the average. Okay. So we want to calculate this. Now we have seen that the probability of a photon getting absorbed after an optical depth tau is e to the power minus tau. The probability that a photon gets absorbed at an optical depth tau is e to the power minus tau. We know this because the specific intensity falls as e to the power minus tau. So that many photons, the fraction of the photons that have been absorbed is e to the power minus tau. Okay, so that's the probability that a photon is absorbed within e to the power at e to the power minus tau at this optical depth tau. So let us ask the question, what is the typical optical depth of a photon inside a medium before it gets absorbed? So that is easy to calculate. We have to do this integral tau e to the power minus tau. We want to calculate the average optical depth of a photon where it gets absorbed, and we have to integrate this from 0 to infinity. Right. So we are considering an infinite medium where every photon will get absorbed. We want to calculate the average optical depth at which a photon gets absorbed. So this is the mean optical depth at which a photon gets absorbed, and this we see is equal to 1. If you just do this integral, it comes out to be 1, right, d tau. Right, so you have to integrate over all possible optical depths, and this integral comes out to be 1. Now the mean optical depth we can write as the mean free path, the mean value of L, the distance it propagates, into the absorption coefficient. So this is 1. That's the definition of optical depth. Right, optical depth is the distance into the absorption coefficient, and the mean optical depth is then the mean distance into the absorption coefficient. We are assuming that this is a constant throughout. So here we see that the mean free path is essentially the inverse of the absorption coefficient. And okay, a point I forgot to mention, the optical depth is dimensionless. The absorption coefficient has dimension of 1 by the length. Okay, that you can check from the definition, and the mean free path is 1 by the absorption coefficient. That's the mean free path of a photon in a medium. And if the absorption coefficient, there is no mean over here, it is just the mean free path is at a particular frequency nu is 1 by the absorption coefficient. Okay. Finally, let me discuss one more thing very briefly. The question is, when a radiation propagates through a medium, so it transfers energy to the medium. Now if it transfers energy, we know that a photon also has momentum, and the energy and momentum are related as E P is equal to E by C. So we ask the question, what is the force exerted by the radiation to the medium? Okay, force per unit volume. So that force in a medium, so when radiation propagates through a medium, not all of it gets absorbed in one unit volume. The part that gets absorbed is essentially I nu into the absorption coefficient alpha nu per unit volume. That's what gets absorbed, and this has a direction of propagation n, that's the direction of the force. So if you want to calculate the total force on a volume element dV, you have to integrate this divided by c over all solid angles. Right, this is the radiation force on some medium. So when a medium absorbs radiation, it also absorbs momentum, and you have a force, net force. You can have a net force. If the radiation is coming from one direction, you will have a force in that direction being acted upon on the medium, being acted on the medium because of the incident radiation getting absorbed. Okay, and this is the force. It is the incident radiation specific intensity into the absorption coefficient divided by c, because that's the relation between the momentum and the energy, integrated over all solid angle. And n is the direction, so you have to consider rays in all directions. Okay. So let me end today's class over here. Tomorrow we shall continue our discussion of radiation a little further.